Hello everyone. This talk is about causal and non-causal tail processes and how they help us understand bubble and crash patterns generated by heavy-tailed mixed autoregressive processes. It is based on a joint work with Christian Gureriu and Yang Lu. Let us start with the motivation for this work. Many macro and financial series display recurring shapes, asymmetric peaks and troughs, short local trends, speculative bubbles followed by abrupt corrections, sometimes flash crash type episodes. In standard Gaussian linear dynamics, these paths are atypical unless we introduce non-stationarity or explosive roots. The key message here is that with heavy-tailed innovations, a strictly stationary mixed causal, non-causal autoregressive model, our MAR process, can generate bubble crash-like episodes endogenously. The mechanism is extreme value driven. An extreme observation is typically produced by a single dominant shock, and the linear propagation on both sides of time creates a quasi-deterministic extreme path. We therefore use the spectral tail process framework from extreme value theory to extend earlier econometric results, describe extreme trajectories, obtain an interpretable turning point logic, and design diagnostics that distinguish pure causal from pure non-causal dynamics via residual plots. Here is the roadmap. We have just started with motivation and key idea that bubble and crash patterns contain information about the direction of shock propagation. Then we recall the spectral tail process for heavy-tailed linear processes, the EVT object that captures the shape of an extreme episode after normalizing by an extreme observation. Next, we specialize to MAR processes, which combine a causal polynomial in the usual lag operator with a non-causal polynomial in the lead operator, yielding a two-sided moving average representation. We then study the one-step conditional distribution of the spectral tail process, because this is the key building block for extreme forecasting. After that, we translate the spectral results into conditional laws for the original process one step ahead, given that today is extreme. This is where bubble continuation versus crash branches arise. Finally, we present causal and non-causal residual plots as a practical diagnostic, illustrate them with a case study, and we close with conclusions and open directions. Let me now recall the extreme value representation for heavy-tailed linear processes, because MAR models inherit it through a two-sided moving average form. Let us first consider a general setup for our basic object, a two-sided linear process. We write YT as a bilateral moving average of IID innovations, with coefficients CAH over all integers. Innovations are assumed regularly varying. The tail of the absolute value of epsilon t decays like a power law with index alpha, up to a slowly varying factor, and we allow tail asymmetry through the limiting probability that epsilon t is positive when it is large. A mild summability condition on the coefficients ensures strict stationarity while preserving heavy tails for the marginal distributions. The central insight for linear processes is the single big jump principle. Conditional on YT being extreme, the event is typically driven by a single innovation term in the moving average. Once that dominant epicenter shock is identified, the rest of the extreme trajectory is almost deterministic, because the linear filter propagates the shock forward and backward through the coefficients. This is the starting point for the tail process representation. Start from an extreme event at date t, assume that the absolute value of the process at time t is above a very high threshold, and let us have a look at the whole rescaled trajectory across all leads and lags. Under regular conditions known as multivariate regular variations, a well-known result in extreme value theory is that the process of the ratios of type yt plus h over the absolute value of yt weakly converges to a process known as the tail process, which contains both the information of the sign and the relative magnitudes along the episode. The spectral tail process goes one step further and removes the remaining absolute scale, so it isolates shape only. That is why it is the key object for forecasting. Many extreme regime questions are about how much larger is tomorrow than today, or more generally about successive growth factors. Those depend on relative shape, not on the particular size of the extreme that triggered the conditioning. So, intuitively, the tail process answers what does an extreme episode look like, whereas the spectral tail process answers how does the episode evolve from one step to the next in relative terms. Now let us focus on the specific case of the heavy-tailed two-sided linear processes. Under regular variation, an extreme value of the series is typically produced by one dominant innovation term in the moving average sum. All other terms are negligible at the extreme scale. This is known as the single big jump principle. Let us assume that the index n gives the index of the innovation term that generates the extreme values of the process. It is the epicenter locating the innovation that drives the episode. Conditional on the pair, the extremal sign and the epicenter, the entire limiting path becomes deterministic. Each maturity h is obtained by multiplying the sign by a simple ratio of moving average coefficients. So extremes generate only a countable family of possible shapes, indexed by n plus a random sign. This is exactly why bubble crash patterns can be classified. Once you know which epicenter is active, the extreme trajectory is essentially pinned down by the linear coefficients, and randomness remains only through the discrete choice of n and the sign. Here we get explicit distributions for the two random ingredients of the limit, the epicenter index n and the extremal sign. The probability that the dominant innovation occurs at position j is proportional to the absolute moving average coefficient at j raised to the tail index alpha. Coefficients with larger absolute weight, amplified by heavy tails, are more likely to generate the extreme. After normalization, these probabilities sum to 1 over all integers, yielding a discrete distribution on z. Separately, the sign of the extreme is inherited from tail asymmetry of the innovations. Pi is the limiting probability of a positive innovation given a large absolute innovation. A key simplification is that n and the sign are asymptotically independent, so the limiting structure factorizes into where the shock hits times what sign it has. In practice, this lets us study turning points through n and skewness through pi almost independently. This separation is useful when we later interpret a symmetry between boom-like and crash-like extremes. This slide explains why ratios, gross returns, are natural functionals of the spectral tail process. Define the one-step gross return as tomorrow divided by today. Under extreme conditioning at date t, these successive returns converge in law to a limit that depends only on ratios of consecutive moving average coefficients evaluated around the epicenter. In particular, the one-step ahead limit is the coefficient at n plus 1 divided by the coefficient at n, so it is a discrete mixture over the possible epicenters. Econometrically, this is the primitive behind bubble continuation versus crash branches. Different epicenters imply different next step multipliers. So once we characterize the distribution of n, we automatically obtain a predictive distribution for the next return in an extreme regime. In the Mar sections later, the coefficients have geometric forms, and the mixture collapses to a small number of dominant return values with weights driven by parameters and by the tail index. This section moves from generic two-sided linear processes to mixed causal-noncausal autoregressive processes, or Mar models. The key point is that Mar processes admit a two-sided moving average representation, so all the tail process and spectral tail process machinery applies directly. What changes is interpretability. The causal polynomial governs how shocks propagate from the past, while the non-causal polynomial governs how the same shocks appear to propagate from the future in calendar time. In the next slides, I define the Mar-PQ model, introduce its pure causal and pure non-causal components, and show how the tail process splits into regimes separated by a random switch time linked to the epicenter index. We now define the mixed causal-noncausal autoregression, denoted Mar-PQ. It is written as a product of two stable filters, one in the lag operator, capturing standard causal dynamics, and one in the lead operator, capturing non-causal dynamics. The stability assumption, roots outside the unit circle for both filters, ensures strict stationarity, yet the model is not purely backward-looking. The key practical interpretation is the causal part explains how past shocks affect today, whereas the non-causal part is a way to encode how today's observation contains information about shocks that will materialize in the future in calendar time. Importantly, for our purposes, strict stationarity implies that the process can be inverted into a two-sided moving average expansion with coefficients indexed over all integers. Therefore, extreme events in Mar models can be analyzed with the same SBJ and spectral tail process tools as for general two-sided linear processes, but now the coefficient structure is tied to economically interpretable parameters. This slide introduces two pure components that disentangle the model. First, apply the causal filter to the series. This produces a component that is driven by current and future innovations. Hence, it is purely non-causal. Second, apply the non-causal filter. This yields a component driven only by current and past innovations. Hence, it is purely causal. In the slides, these are labeled as equations. Here 1 and 2. The important message is not the algebra, but the direction of information flow. The non-causal component is predictable when you run time forward only if you condition on sufficiently rich information, because it depends on shocks that have not yet occurred in calendar time. Conversely, the causal component behaves like a standard stationary armor-type object. Later, when we look at extreme episodes, these two components will allow us to see which side of the peak is explained by past shocks and which side is explained by future shocks, providing a structural interpretation of bubble buildups versus crash unwindings. Here, we connect the MAR model to the two-sided linear process framework by constructing its moving average coefficients. The idea is to invert separately the causal filter and the non-causal filter. Each inverse has a one-sided power series expansion. The causal inverse produces coefficients that live on non-negative maturities, while the non-causal inverse produces coefficients on non-positive maturities. In the slide, these expansions are numbered, 3 and 4. When we multiply the two expansions, we obtain the bilateral moving average representation of y at t and an explicit formula for each two-sided coefficient CAH as a convolution of the two one-sided coefficient sequences. This step is crucial. Once the coefficients are available, all extreme value objects, epicenter probabilities, spectral shapes, and limiting ratios are functions of the CHHs. So conceptually, MAR extremes are not a new EVT theory, they are the usual SBJ mechanism applied to a specific structured family of two-sided coefficients implied by the causal and non-causal polynomials. This slide explains how the pure component's moving average coefficients relate to the global two-sided coefficients. Introduce a lag operator acting on maturity indices, so shifting H shifts the coefficient sequence. With this notation, the coefficient sequences of the pure non-causal component and the pure causal component are obtained by applying the causal or non-causal polynomial to the global sequence. The listed properties have a clear meaning. After filtering, one component has support only on non-positive maturities and the other only on non-negative maturities. So the pure non-causal component collects what is driven by present and future innovations, while the pure causal component collects what is driven by present and past innovations. This separation carries over to extremes. After normalizing by an extreme yt, we can project the extremal trajectory onto these two directions and diagnose which side of the episode is generated by which component. Now we move from the process level to the tail process level. Condition on an extreme event at date t, and normalize all maturities by today's magnitude. The claim is that if you apply the same filters to this normalized extreme trajectory, you obtain limiting objects UH and VH. These are, respectively, the pure non-causal and pure causal components of the tail process. Intuitively, the tail process XCH describes the full extremal path around the extreme date. By filtering X to REH across maturities, we separate the part of the extremal path that is compatible with a purely forward propagating causal mechanism from the part that is compatible with a purely backward propagating non-causal mechanism. This is important because in MAR models, an extreme episode can look like a bubble that builds up and crashes, but the build-up and the crash are not symmetric. Different parts of the trajectory are explained by different innovation timing. The decomposition into U and V is therefore a structural EVT tool for identifying which side of the peak is past-driven and which side is future-driven. This proposition provides the turning point logic. Under the SBJ representation, the extreme episode is driven by a random epicenter index n. Away from the maturity location h close to -n, the normalized tail process satisfies deterministic linear recursions. On one side, the non-causal filtered component is forced to be 0. On the other side, the causal filtered component is forced to be 0. This yields two regimes. In the pure causal regime, for maturity sufficiently after the switch, the non-causal tail component vanishes, meaning the extremal path there is compatible with a standard causal propagation. In the pure non-causal regime, for maturity sufficiently before the switch, the causal tail component vanishes, meaning the path there is governed by the non-causal structure. Around the switch region near h equals -n, both components can matter. This local interaction is what generates peak timing and the apparent bubble crash turning point. So the epicenter index does not only pick a spectral shape, it also determines where the regime changes along the episode.